Hey everyone, thanks for attending this talk after your high sugar lunch. I hope the sugar crush is not going to hit you too badly. I'm going to do my best to keep you awake for this next 40, 50 minutes. Why are you guys here? So, this talk will cover a big chunk of the forensics toolkit we use at Google. Just so you know, it's all free and open source software, so my goal here for you guys is to learn that A, these tools exist, and also B, that see how maybe you could use them in your own ecosystem. Because showing a bunch of slides about tools is pretty boring, I thought I would kind of invent a scenario where these tools are being used to chase down bad guys and solve a case. So we're going to talk about GR. Most of you know GR. Who knows GR? Awesome. Who knows about Plazo? Pretty good. Who knows about TimeSketch? Okay. Who knows about DF TimeWolf? Ah, got you there. That's normal. I never talk about it. This is the first talk I do about it. So who knows about Turbina? No one? Great. It hasn't officially been released yet, but there's a repo there. So there's an open source repo, so if you guys had done your homework, you could have maybe found it. But anyways, that's a lot of tools to cover. I'm going to go pretty fast, I guess. I don't know. We'll see how that goes. But in any case, I hope you will remember this. They will come up throughout the presentation everywhere. So why am I giving this talk to you? Well, the main point is I'm one of the DF TimeWolf core developers. All these are tools that are used with our team, within our team, and that have been written by us, except for GR, who has its own set of team. But in any case, I do digital forensics and incident response at Google, and we're in this sweet spot where we can write our own tools and we get to use our own tools. So we know exactly what kind of problems we have, we know exactly when our tools don't work, and we know exactly who to ping to fix bugs. So that's pretty cool. I love to write code. I hate doing boring, repetitive tasks. I like to do forensics. I like to hunt bad guys. And my mission is try to kind of automate myself out of a job so all the tools do the work for me, and I can just hang out with my friends and drink beers. So as I said, my goal is not to bore you. So let's start kind of build your own adventure with this guy, cyber hacker, or whatever. So the scenario I'm going to showcase today, and this is really important, none of what I'm about to describe is true, except for the demos that you'll see. Those are true. But the scenario is completely invented. So who's our victim today? Our victim today is Greendale Polytechnique. So it's a very famous Swiss university. They specialize in setting up air-conditioned units in big companies. It's a very complicated job, so they have a five-year program to teach that. And anyways, so everyone is on semester break. You know, the heat is starting to come in. Everyone is having breakfast in the street, and then someone gets a tip about a domain that's being used in a phishing attack. So Greendale XYZ. So Greendale is a university. They have no proxies. They have no logs. They have nothing. The only thing they have is GR, and you'll guess, a bunch of open source forensics tools. So quick word about GR. GR is agent-based. I'm going to go through this real quick because you guys know about this. It works on almost any platform, Windows, Linux, Mac OS. It's basically something, an agent you can query and tell it, okay, give me files, give me these artifacts, and you can query individual hosts in your network, or you can query your whole fleet. That's what we call hunts. This becomes very relevant when your fleet has 200K machines. You need to have a lot of science to not kill your command and control server, if I can call it that way. So yeah, it does file collection, it does artifact collections. What are artifacts? Artifacts are a very specific thing in GR. So it's basically a collection of, you see, for example, this is a user shell history is one of the artifacts. It's a file type, and it has a few paths that it's going to try to collect. So if you tell an agent, okay, give me the user's shell history for this host, then it's going to fetch these files And if they don't exist, you'll get nothing. If they exist, then you'll get those. You can also combine artifacts like this using these names of artifacts. So in that way, you can build pretty complex structures of things that from a user perspective are pretty easy to query. I mentioned Plazo a while earlier. So Plazo is basically a super timeliner for your system. It's going to go through your file system, and it's going to parse every single file it knows how to parse. And that is a lot of different types of files. It's going to, if it finds a zip file, it's going to parse your zip file. It's going to open the zip file. It's going to see what kind of files you have in there. If you have a zip file in a zip file, it's going to do the same thing. If you have a log file, an Apache access log file in a zip file, then it's going to parse that file, and it's going to extract timestamp information and other kind of metadata that the file has. And with all this, what you will end up is with a system timeline. Some of you guys who have taken SAMS courses maybe know this as a super timeline versus a file system timeline, which is a bit more simple because it only considers the file system. This will do a timeline of everything that's on your system. If your bash history, for instance, has timestamps, it will parse those, and it will know where to place them in your timeline. So Plazo uses Plazo files. It's a SQLite-like format to store information. You can also use psort to get a CSV, but who likes to use CSV? I know that most forensics people only know about grep, cut, and awk, and that's all you need to do 80% of the cases. That's why I use most of the time. But if you're really fancy, you can also use TimeSketch, which is basically a forensic timeline visualization tool. And you can issue nice queries here. Well, you can't see anything, but you'll see them in the videos I have set for you. And you can also see here, you have different colors. They each correspond to a different system that Plazo has analyzed. So that way you can really cross-reference and cross-correlate events that happen in different systems that have been collected into the same, as we call it, sketch. So it plays really well with Plazo. It's made to ingest Plazo files, so you don't have to send a bulky CSV file. It's also multi-user, so you can set permissions on timelines and such. It's multi-case, so you can have different cases on the same TimeSketch infrastructure. And as I said here, it's multi-timeline, so you can see where events in different systems coincide. Now, DF TimeWolf. This might be more interesting for you guys. So DF TimeWolf is basically a CLI tool that acts as the glue between GR, Plazo, and TimeSketch. Because otherwise, what you would have to do is open your browser, go to the GR interface, select the kind of hunts you want to do, select which host you want to run them on, select all the artifacts. Once you have that, you have to wait until it runs, then you have to download the thing again, you have to send the thing to Plazo and then to TimeSketch, and that's a bit annoying. So DF TimeWolf does all of this with a single command. And because it's not the only systems that we have, we built it in a way that you can extend it pretty easily. So that's where we have modules, and each module is a way to interact with another system. So you can have collectors for GR, for example. You'll have processor modules for Plazo, and you'll have exporter modules for TimeSketch. And you can have any kind of module you want. You can have a reporting module. I mean, we can go on, and I'll go back to this later. How these modules are chained is defined in recipes. So it's just basically a way to say, well, the output of the GR module just feed it into the Plazo module, and the output of the Plazo module just feed it into the TimeSketch module, as we can see here. So this is a regular invocation of how it works. This is binary. This is the recipe name. This is the host you want to collect information from. This is the comment, because the recipe has a comment argument that you can use. And this is the sketch ID. All this is defined in basically in the recipes. And this is how it works. So the GR collector is going to get this information from the command line, and it's going to generate this path, which contains whatever information GR sent back. This is going to be fed into the Plazo module, which is going to feed back another path, which is the Plazo file that is generated by Plazo. And this is going to be sent to the TimeSketch module, which is going to process it, and the module is going to send back a nice URL with a timeline description. So all these modules, I mean, you can build as many TimeSketch modules as you want, and they will all do different things. and that'll be great. This is the one that we have that we use that is on GitHub, so this is a good example of how it works. This is what a recipe looks like. So in blue, you have the recipe name. In red, you have the collectors, which are just Python classes. And in green, you have the arguments that each one of those take. So these are command line arguments that can be specified in the command line invocation or in a config file. I won't go into too much details in there. Anyway, so back to our case. We know about this Greendale domain, greendale.xyz, which is actually Greendale because there's only one E. So smart people that are maybe trying to target us. So in this case, since it's a phishing, since the tip came in saying, oh, you got a phishing domain there, we're going to ask to look for browsing history artifacts. So this is how it works. So df_time_wolf is going to say, is going to tell Gerd, like, okay, hunt for these browser history artifacts. A fresh reminder, browser history artifacts are just a collection of file paths for the history files of major browsers like Chrome, Firefox, Internet Explorer, Edge, whatever. Gerd is going to tell all its agents, like, okay, do you know about browser artifacts? Can you send me any data? And it's going to return a hunt ID directly to df_time_wolf. This is asynchronous, of course, because you don't want to wait for 200K nodes to return before you can get a hunt ID and go on with your work. So let's see if this works. This is supposed to be higher quality. There you go. Can you guys see? Okay? Great. So this is the help menu. You can see all the recipes are in here, and there's a help text. You can see the arguments are here, and they will be passed in the command line in here. As soon as I paste it, there you go. So it starts a collection, the hunt. It says, okay, these are the artifacts you want me to collect. Those are the ones I passed on here. And the hunt was created successfully. Here it is. There you go. You can move on with your life. What? Okay. So we have this. Now we have our hunt ID. We need to recover and get the results of that hunt. We're going to use another recipe for that, which will basically ask Gerd, hey, Gerd, do you have the results of that hunt? And Gerd will say, yeah, sure, here's a zip file with all the things you asked for. We get the zip file, we push it into Plazo, and then we send the Plazo file to TimeSketch. This is what it looks like. So use the hunt ID here. It's going to run this command, get the files from Gerd, the zip file, and then it's going to run the external command, log to timeline.py with these arguments. There's a log file. There's a Plazo file it's going to generate, and it's going to send. It's going to give you this URL, as we've seen in the first command line demo I showed you guys. So once we have this, then we go to TimeSketch. And how do we use this for investigation? So this is what the sketch investigation looks like. So you have your hunt results here. This is a timeline that we're interested in. It's the only one that we have also. And now we can just look for our domain. So this is going to parse all the things that we saw here, all the users' browsing artifacts. This was a demonstration, so there's only one, of course. If we dig into the browsing history, you'll also see me trying to figure out how to install GUR and such. But this is basically the file that's been downloaded, and that's interesting for us. So we can start relevant events, and we can do a bunch of stuff in TimeSketch. We can also search for academic calendar.zip, and then we see that we have another bunch of things. Why isn't it pausing? There it is. We have a lot, last visit time, last check time. If the timeline was more real, then we would have a bunch of other websites in there. But the thing is, you can write comments on every event. This is pretty bad, right? You can go on, and you can also select events that will then go into what we call a saved view, which is basically a part of a TLDR of your incident. So if we scroll there, so I'm saving this, I'm selecting the events and I'm saving them as a save view. And then, and this is a pretty cool thing, a pretty cool feature that that TimeSketch has, is stories. So stories are a way to just tell what happens in your incident. So you can start saying, oh, yeah, well, I dug into this tape, we got something bad, I did some searches, and let me show you this. So you can include in your report any saved view that you want. So in that way, you can like really have this written prose for anyone else who's going to keep on digging into your incident later on, or even yourself when you get back to it the next day, because this guy is headed home. And you can really use this to make a clear message of whatever it is that you want to convey. So what do we know so far? So in our case, at least one person downloaded greendale.xyz academic calendar.zip. The zip file contains a calendar.js file, and is it really a calendar? A JavaScript calendar? I don't think so. It's probably more like a stage 1 dropper. So if we open the file, then this is what we see. And this looks pretty bad. It kind of looks like a URL. Can anyone guess what the encryption is on this? Almost. It's ROT 14. Ha! Yeah, that was easy. Anyways, so after some very advanced deobfuscation, you come up with this student-greendale.xyz domain, which kind of looks sketchy because it's not from Greendale. You have like a app data roaming startup keep.bat path in here. And more worrying is this, which is basically checking if the domain, the AD domain that the user is on, has Greendale in it or not. So as far as targeting goes, this is pretty targeted, I would say. So maybe we should dig a bit deeper. So we have our JavaScript dropper. The JavaScript dropper drops a secure.script URL into a keep.bat startup file. So now we want to know if anyone executed or downloaded this file. So we're going to use another set of artifacts, these persistent mechanisms, shell registry files, and Windows system registry files, because we have a bunch of good things that can tell us if we're being owned or not. So this should look familiar at this point. You have here the host that we're targeting, because there's no point in searching for all these things everywhere else. And you can see that we have our client is here. Oh, there's a GER client. We've last seen it on this day, so 0 minutes ago. That was when I ran the video. These are the artifacts that we want. So we're going to schedule this. And since it's a targeted collection, so we're just asking for a specific host to return information, DF time will wait until this is finished. You guys probably don't want to wait. So I'm just going to fast forward here. It's going to go through Plazo. It's going to process this. So this goes a little long. It takes a little longer than the simple browsing history artifacts, because there was only one browsing history in the hunt you saw, and it was fairly small. This is a bunch of registry keys on a Windows VM I've had for a long time. So it takes a bit longer, and it ends up in the same sketch, number 31. And this is how the investigation in TimeSketch would look like. So at this point, with just one command line argument and invocation, we ended up grabbing information from a remote host, and it's waiting for us in TimeSketch to be analyzed. So here I'm showcasing the search templates. Search templates are a pretty cool feature of TimeSketch where you can use collective knowledge of your teammates who work in forensics as well, and they can say, oh, well, I know about startup items, and I know where they are. So instead of you having to look up in forensics wiki or whatever, the file that you need to recover or that you need to search for, then you can only use, you just have to use this in here. You can add it to one of the views of the sketch. And, well, of course, this is pre-made. But this is the app.compat cache, cross-referenced with startup. So this is exactly where the keep.bat file would stay. And here we see like, oh, there's a very interesting information. So the file was indeed executed. As you can see, this is the full thing. So this is the cached entry, and this is the full path of what was executed. So this is also pretty interesting information. We can add it to we can select it, add it to a saved view. Like, okay, this is keep.bat running, so we should probably pay attention, or keep app.compat, whatever. If we go to the story, then we see our previously saved work, and then we can keep adding more stuff as we go on. So this was installed. I will add the app.compat, and I will switch to the next slides. So what does keep.bat have? This is a PowerShell script, and this is likely very advanced encoding. It's base 64, it's not base 65, don't worry. So what you see here is, this is basically a PowerShell Empire script that grabs stuff from here and probably does very bad things with it. And this is a key that it uses to authenticate. So at this point, we can determine that our attackers, whoever's attacking us, really wants something out of us. But what? Anyways, let's try to take a step back and summarize what we have for now. We have some IOCs. We have the two scripts in the Greendale XYZ domain. One of them is kept as a keep.bat script in startup as persistence. And they all call back as a C2 to this legitimate businessman's .club. Interesting. Everything is fine. We're not getting owned at all. Very few students fell for the first scam, but we have a hunch. So we go there and we see, oh wait, look, there's a bash.sh script here that we haven't seen so far. That's pretty interesting. So we put on our best VPN client called ping and a hoodie, and then we can grab the file from the server. And again, we have this very advanced base 65 encoding that is this time piped into Python. And we deobfuscate it, and we see that this is the same C2 URL with this time a different key that seems kind of generated the same way. This is an encryption algorithm. I would guess it's RC4, but I don't know. So now we want to know, does this bash.sh thing has been executed anywhere? And this is where I spoiled the fun a while ago. We're going to do a query with all users' shell history. The hunt was created. Oh, that was it. Okay. Small problem with chaining the videos. So now we run the Gerhunt downloader, which is going to download the results of the hunt that we specify here. They're all going to run full Plazo, and it's going to output a very nice timeline, I guess, somewhere. Did I cut the video too early? I didn't. Oh, yeah, there it is. So we always download the same thing into the same sketch. So if we go back to time sketch, we see this is fairly interesting, because you can see that in here now we have like 3 different timelines, and they all correspond to the 3 hosts that had bash history included in them. And we can query the whole sketch. So all of the timelines, we can query them simultaneously. And this is why you see different colors here. They all correspond to a different timeline. So if we look for bash history command and bash.sh, then we'll see like, oh, well, someone executed this. This doesn't look good. Yeah, this is bad. This is bad. The script ran. So we even have the client ID there. We know the file where the information came from, and we're going to save this view again so that we can keep it in our report. We can also we can also check if other curl things happen. And well, this is kind of hacky, right? This is just to show you guys that if you search for curl, you'll see all the curl commands that have been chained in different hosts. And here you can see all the commands that I use to install my my Gert client on my different instances. So you can see I was working between 215 and 220 a few days ago for this. This is proof. And you can add, as I showed before, the things to the story, and you can also have a very fancy thing with bold text and stuff. This is Markdown, so you can edit things as you want. So we have one hit, but the thing is, we'd like to dig deeper into this host to see what else happened. The problem is, well, Greendale has been migrating all their infrastructure to the cloud, right? In the cloud, everything is good and fluffy and fresh, but sometimes bad things like this happen. Of course, not any cloud, but GCE. So that's Google's cloud, of course. Can DF TimeWolf help? Of course it can. So this is a module that hasn't been open sourced yet, but it will be as soon as the code is a bit cleaner, and we intend to make it cleaner. But what it's going to do, it's going to just query the cloud API and issue a snapshot of the disk that you want data from, and it's going to make a copy of that disk, so then you can analyze it. You can either download it back to your computer and analyze it using, mount it, using mount, or if you want to go run it through log2timeline or grep or whatever, you can do it. So this is the disk being copied. This is fantastic, very thrilling things. And there you go. The end result is, well, you have a VM in your cloud project. So here you say, oh, I want to use this recipe. I want to use this cloud project, and I want to spin up this VM. So you have a Greendale analysis VM, which is GCP forensics, and then you have this, which is the name of the disk that has been created for your analysis. This particular recipe spins up a VM, attaches the disk to it, and lets you SSH into it and carry out all the forensics that you want. But in this case, we're going to go a bit further, and we're going to talk about Turbinia. So Turbinia is a new system that we're building that is just about to be released. It's basically automation of forensics tasks, but in the cloud. So it lives in the cloud, and you can ask it questions. You can tell it, hey, I have a GCP disk somewhere, and I want you to process it with whatever modules you have, like Plazo, and then please dump the results into TimeSketch. So you've seen a couple of diagrams before. This one is a bit hairier. This is the computer that we want to forensicate. It's in the cloud. It does not exist, or we don't know where it is. This is its disk. This is Turbinia. This is Turbinia storage, and this is the disk it's going to create. So the first thing DF TimeWolf is going to do is going to ask the cloud, whoever that is, please copy Greendale admin's disk. The cloud is going to say, sure, here's the disk ID that you need. And then DF TimeWolf is going to go ask the cloud again, or in this case, more like ask Turbinia, please forensicate this disk that is here. Turbinia will run, and it will return after some time saying, okay, now the Plazo file is ready for you. It's in this cloud bucket, so feel free to grab it. And then DF TimeWolf will continue its run through Plazo and to TimeSketch. Well, in this case, yes, you don't need Plazo. You can go directly to TimeSketch. Eventually, we want Turbinia to be able to send results to TimeSketch directly. But for the purposes of this demo, I wanted to showcase this. You can also use DF TimeWolf as a very simple script to just upload arbitrary files to TimeSketch. And when I mean arbitrary files, I mean you can upload anything, but all that TimeSketch will understand is CSV files and Plazo files. So you use the TimeSketch upload recipe, which is very simple. It just reads a file from the disk and sends it to TimeSketch. But it's also pretty easy when you don't want to spin up a new browser tab and send the things yourself. So you create a new sketch, or if you had passed the sketch ID parameter, it would have added the things to an already existing sketch. And now it's just going to export things to that sketch And whenever time sketch is done, it's going to reply with the ID of the sketch that was generated. So far, we're being pretty agile. The disaster was averted, yes, because, of course, once you do the forensics on that disk, you realize that there wasn't any trace of lateral movement, and also Greendale users all use 2FA tokens, so that's pretty good, and that kind of thwarts phishing in a way, so I would recommend you guys use it if you don't. It's really good. So after some analysis, it was determined that the attacker's objective was likely to disrupt the launch of Greendale's new PhD program in AC flow study, which is very secret, and we wouldn't want other universities to copy on us. So this is about all I have for you guys today. I was maybe a bit quick, but if I want you guys to remember something is, all these are tools that we are working on. All these are tools that our team is using daily. So I really hope that you may find use in them, and they're all open source. You can grab them, you can play with them. We accept pull requests. We encourage contributions. Maybe Google has a reputation to be very strict with code. It's true, we don't like bad code. But we won't shame you, and we really encourage contributions, even if it's something you've forked the project, you've worked on something, it's not great quality, just send it to us, and we'll see if we can make it work and integrate it into our master branch. Because I think this is something that is very, for now, Google-centric, but we've made it so that other ecosystems can also benefit from it. And as I said, yes, it's all Apache 2 license, so this is usable by anyone. And stuff I haven't covered today, so other things that these tools can use and that maybe you can use as well is memory analysis for Gur. It does also some host timelining, so if you don't want to recover all the things, all the artifacts or all the disk, then you can tell it, okay, just show me a timeline of this directory and its 5 subdirectories or something. You can also run custom Python scripts. Plazo, well, I showed you what it can do, but it can parse a lot of formats. Lots of them. There's a lot of people working on, Labial and trying to figure out how to parse things. There are new parsers integrated, I would say, every month or maybe every 2 weeks or so in average. DFTimeWolf, well, I've showcased a few of the systems it interacts with, but it can pretty much interact with anything that has an API. You could imagine DFTimeWolf asking for a Plazo file from Plazo, and then maybe cross-referencing that with a threat intelligence database so that you don't even have to click on saved views in TimeSketch anymore, and you can just have automatically things that are being tagged. That would be cool. And that might come later this year. Who knows? TimeSketch has a few things, and this is something I can show. It has a heat map view of a, So this is demo.timesketch.org. You can all play with it. There's a very secure interface, as you can see. But it has a few cool things, and it's a good way to play with a version of TimeSketch that has data in it. So if I go to charts, I can see okay, so this is EVTX records, identifiers. So this is probably login and login type, interactive, and that kind of stuff. So what you get from this is we're basically trying to understand who's logged into our systems. And you can see this timeline. Maybe if I zoom out a bit. Oh, okay, great. This is reactive. So anyways, you can see this view that tells you, hey, you've been hacked here. So there's a huge volume of logins here. So this is probably where you want to investigate. And you also have some graphs. And these are a pretty cool feature. So if we want to see all network logins, 20 minutes within, 20 minutes one from each other, this is what you'd get. Can you see anything? Oh. There. So you can see that this Beachon user logged into the registrar computer and also into the DC1 and then student PC1 network. And all this is from the same session, or at least all these login events are 20 minutes apart. So this is also a nice view of all your logs that you probably didn't have before with a linear log analysis, like you could do with with Plazo, CSV files, and grep. I'm zooming out. How do I present here? Okay. I'm going to zoom out until it's big enough. So this is my last slide anyways, I think, yeah. So this is where to find us. We're mostly all on GitHub. Some of the projects are under the Google main repo, like Gur. You also have Log2Timeline and Plazo. Log2Timeline has its own repo of things. It is where you will find documentation about the tools. It is also where you will find dfTimeWolf, which has a pretty cool logo, just like Chopitea, which looks kind of like a flying ham. We're really not good at logos. This is really bad. Plazo, I don't know if you can see it from here, but it's like literally a super log. So you also have TimeSketch is under Google. And all these projects are for you guys to hack on, contribute, and use. And hopefully you'll get something out of those. And yep, that's it for me. So if you guys have any questions, I'll take them now. Thanks.
Awesome. Thank you very much, Tom. A really great, interesting presentation again. Does anyone have any questions at all? Please raise your hand and I'll come to you. Someone's got to have something. Come on, forensicators. Good.
Thanks for the talk.
Thanks.
I'm sure it's a thing you've thought about, but there have been a couple of stories recently in the news about parsers having exploitable bugs. And when you say, and repeatedly said, Plazo parses everything.
Yep.
Is there an issue there? How do you deal with that?
So it is an issue. The easiest, the most straightforward way to patch this or to circumvent this issue is running Plazo in like secure containers, or at least a sandbox of some kind. So even if you get maybe code execution somewhere, if you run it in a container that doesn't have internet connectivity, then you limit the risks a lot that your evidence leaks. And of course, we don't want the attackers to hop onto the rest of the networks. So yeah, running Plazo as root on your production machines is probably not a good idea. But you can probably work around that pretty easily.
Hi, Tom. Thanks for the talk. Is Gur able to parse Yara rules on files or memory or anything? Can you deal with Yara rules for scanning?
Yes.
Gur?
Gur can ingest Yara rules, and it can scan process memory with those Yara rules.
Cool. Any other questions?
Thanks for an awesome talk. The last time Daniel White presented Plazo and TimeSketches with Cyberstorm 2 years ago, he lured me into installing this. And I spent like one day trying to get Plazo and TimeSketch up and running. I gave up. Could you say anything about the maturity of the code and the products?
So, all right, I have a comment on that. When I started at Google, I was just like you. I was like, oh yes, Plazo looks awesome, but I don't want to spend half a day installing it. Same goes with TimeSketch. And honestly, so maybe it's because now I'm using these tools much more often. But for this demo, I got Gur up and running in 5 minutes. I got Plazo up and running pretty quickly. More than 5 minutes, but still pretty quickly. And TimeSketch is way easier to use now that it has like Docker containers and background files and that kind of stuff. So all of these projects, I guess we like to push code early, but they're all gaining in maturity. And I know that my teammates have been working, Daniel has been working a lot on, end-to-end testing of everything to make sure that we root out a maximum of bugs. But yeah, I would say that they have definitely matured.
Cool. Anyone else? Any more questions? Last opportunity. Looks like they're being nice to you, eh? Cool.
Yep.
All right, thank you very much, Tom, once again. Round of applause, please.
Thank you.